dear. So in the previous module we have already studied that operational amplifier can be used as a differentiator or differential circuit. Differential mathematical operations can be possible by using this operational amplifier. Now I am again just make it I am just at the last time you can understand what kinds of circuit we can study. First we just go for another inverting amplifier circuit and then we will analysis it. So this is the inverting amplifier circuit. This is RF, this is R1, and there is a voltage source, that is suppose V1, and this is negative inverting, and this is non-inverting, and non-inverting is in the ground, and this is the output voltage V0. Okay, in the previous case what I am doing, I am just replacing this particular R1 and just convert it to the with the capacitance. Now here I am doing is the things in something different. I am just change this particular circuit and here I am make it to the capacitance. Okay, very good. If I am changing it to the capacitance, so it is the C suppose, then what will happen? We have already know that in the previous case also we have know the current in here, that is I1, and current in here, that is IF. Suppose this I1 equals to minus of IF, this I1 equals to minus of IF. Here it is IF, we can say that it is the IC because the current is passing through this capacitance, that's why we can say it is the IC. This is the IC. Why? Because this is the same current, actually the inside of the current of the capacitance, which is the current is passing through the capacitance. This is IC. Okay, so I1 equals to minus of IC. Okay, now next, as this is I1 which is equals to minus of IC, then how we can define and justify these things, that is a very important things. So for that point of view, we want to go for some very important calculations of it. First of all, we know that there is one equation Q equals to CV, as same as like Q equals to CV. Q is what? Q is the charge, equals charge and amount of charge, and C and V is the capacity of charge, stability charge, capacitance, and V is the voltage. If I am multiplying these two, what is amount of the charge is determined. So this is the capacitance equations, and from there we can represent that dq dt, which is equals to C dV dt. dq dt, I am just differentiate it for the purpose of getting the current in here, and dq dt is basically nothing which is equals to IC, and for that reasons C is equals to V, and here this V is basically the voltage between this capacitance. So we can write this voltage between capacitance like this way, that is C dV0 dt, C dV0 dt. Okay, that is IC equals to C dV0 dt, like this way. Okay, so we just representing this I1 which is equals to that is V1 by R1, which is equals to minus C dV0 dt, C dV0 dt, minus C dV0 dt. Okay, one expressions is coming at presence now. Whatever our aim is to find out the V0 expressions. In the previous case we also find out the V0 expressions and get one result that input is differentiate. Now there is one term of the differentiations is coming, and I want to just convert the concept, that is I want to determine the V0. So for that reasons, to get this V0 we have some concept of the different integrations, otherwise we cannot get this value V0 properly. So for that point of view, what we can done it's like that way, that dV0 which is equals to dv naught which is equals to minus 1 by r1 c minus 1 by r1 c r1 c v1 dt minus dv naught equals to minus 1 by r1 c into v1 dt. Okay, so basically this is the representations of this dv naught which is equals to minus 1 by r1 c v1 dt, and which is representing like that way. We just integrating these two term, that is integrations of dv naught which is equals to minus 1 by r1 c integrations of v1 dt. That means we can get a result that v naught equals to separately which is equals to minus 1 by r1 c integrations of v1 dt. You show this is the expressions of the integrations of the input terminal, and for that reasons we get the output voltage v naught. Suppose if it is possible that considering or designing like this way, that 1 by r1 c which is equals to 1, it can be possible, it is in our hand. Whatever the signal, whatever the things we just designed, that c value and r1 value like that, so you can develop by that, by which that r1 and c1, 1 by r1 and c1 equals to 1. If 1 by r1 c1 equals to 1, then the expressions is coming like that way, that v naught equals to minus integrations of v1 dt. Okay, minus integrations of v1 dt. So that is the expressions of integration, simple integrations. There is one minus sign, yes, that's true, there is one minus sign, but this minus sign is, we can able to omit this particular minus signs. We can change this minus signs by the sign changer. So you show the input voltage is integrating in here, the input voltage is integrating in here, and get the output voltage, that is the v naught. So we can say represent, this is the integrator circuit by using operational amplifier. So this is the integrator circuit by using the operational amplifier. Now there is one very important thing that I think it is in your mind, that how in case of integrations there should be one constant, there should be one constant. So what is the actually the constant is there? So there should be plus c, that is the constant. You show this plus c is equals to actually the value, that means this is the voltage and this is the plus c equals to actual one value. Value means suppose anything value. So if this is c is the actual anything value and it is the voltage, that means it is DC value. So basically how this particular DC value is coming? This DC value is coming for the purpose of this capacitance. If this capacitance is stored the charge previously, if this capacitance stored the charge previously, this particular value is this capacitive value, this DC value. So each and every integrator there is a constant, that is also mathematically proved. This C value is basically the voltage which is remaining in here. This is the constant C, this is not capacitance C actually. We can represent it as a also, and we can, for your not if you are not confusion, so I am just representing it is a is a constant, and this A constant is basically a DC value. This DC voltage is basically whatever the voltage is already stored by this capacitance previously, that is the DC value. That DC value is representing in here, this is the A, that is the voltage DC. Okay, so this is our representations of the integrator circuit. This is our representations of the integrator circuit. Thank you very much. Hi. So we have already know about the operational amplifier very much, very different things, that is the characteristics. But today we want to know about the quality of the operational amplifier, how we can define the. I'm giving you two. Suppose I'm giving you two op amp, and I'm asking you this question: the quality of op amp, which quality, which op amp is better quality? Then how you can answer practically? How you can answer as an industry person? That things we have to show. So for that point of view, we have to just know about these things like that way. Suppose there is one operational amplifier, that is OP1, okay, and that is also this OP1. There is a non-inverting, inverting, non-inverting, inverting, okay. And there is another operational amplifier, that is OP2. There is also OP2. So there is one amplifier op amp, this is OP1, and there is also op amp, this is OP2. I'm just two times draw this circuit, and I'm just two times draw this circuit, okay. Now suppose I'm introducing one signal in here. At the same signal I'm introducing here. So we can represent it as a case 1, and we can represent it as a case 2, case 1 and case 2. Now I am introducing one signal. The same signal is the non-inverting terminal and inverting terminal, and the same experiment we have to done it in the same signal I am introducing in here and here, okay. What I am doing, I am again repeat that this is the case 1 concept, this is the case 2 concept. There is a op amp 1 and there is a op amp 2, okay. So what I am doing, I am introducing that the signal, that is the same signal in here, in this and this, and here this and this, the same signal. And suppose I am getting a response in here, that is like that, very small voltage, and comparatively this voltage, suppose I am getting the output, this voltage is high, okay. I think you know about that. If I am introducing the same signal of the operational amplifier, same signal of the operational amplifier to terminal, input terminal, then the output tends to 0, output becomes 0, output tends to 0. So for that reasons, you show this output is tends to 0, and this output is also tends to 0. This output is tends to 0, this output is tends to 0, but you show this voltage is much more tends to 0. It's a very nominal than this voltage. You show there is a very small amount of voltage is there than this voltage is greater than this voltage, very small amount of voltage, but this voltage is greater than this voltage. So actually the operational amplifier is working like that way. If I'm introducing the signal of the operational amplifier inside of the operational amplifier, this, for that point of view, what happened, the op amp is try to remove these two signals and get the output. For the differential amplifier we have already studied that. So for that reasons, for the purpose of the quality, for the purpose of the concept of the quality, the concept of the quality, this op amp is much more better quality than this op amp. This op amp is much more superior quality than this op amp. Is not it? Okay. Now next go for this particular case 2 concept. This particular case 2 concept. This particular concept, not case 2, that is the second concept, second concept, and that is also case 2, second phase. That is, I am introducing the signal here, this, and here one antiphase, same antiphase signal I am introducing. Okay, and for that reasons I am getting a signal output in here which is looks like that. And in this side also we done the same experiment. In this side we have to done the same experiment and get this type of output. You show here, this is the antiphase I am representing and get a large amount of voltage. Then if I am introducing the same experiment I am doing in here and same voltage, input voltage I am introducing, but a small amount of voltage I am getting in the output. I hope you can understand these things. On the basis of the concept of the quality, again this particular op amp is much more better quality than this particular op amp, because in the case of difference mode of actions, it give a huge output, but it cannot able to give a huge output. In here it is give a common mode concept and a get a output which is very nominal, but here it is in the difference mode of actions but give a huge output than this. So quality, on the considerations of the quality for this particular experiment and for this particular experiment, both the case, the op amp 1 is better than the op amp 2. Op amp 1 is better than the op amp 2. Okay, very good. One things I want to explain, this is the common mode, as the signals are in the common positions, so this is the common signals which is introduced in the operational amplifier, and for that reason the output tends to 0. So it can be called that the common mode configurations, and you show here the signals is the difference. So for that reasons we can say that is the difference mode of actions. So we can say this is the common mode actions and this is the difference mode actions. This is the common mode actions and this is the difference mode actions. Same like this is the common mode action, this is the different mode actions, because the difference input signals is given and for that reasons the output I am getting, and there is the same input, common input is given and for that reasons the output is getting. So this is the common mode configurations, this is the different mode configurations, common mode and different mode, okay. Now a very important things I am considering, I want to determine the gain in here and gain in here. Gain. If I'm considering the gain, if I want to know about the gain, okay. So you show in case of this gain, this gain is tends to very low. This gain is tends to low, and if you considering this gain is tends to high, you show, because if this is the difference then it is becoming high. So this is called the difference mode of actions. We can say it is AD, and this is the common mode actions, so we can say it is AC and it is AD. AC and AD. This is AC, this is AD. Okay. Now if we can go for one ratio representations of this, that means we just representing it like that way, that mm, that 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 AD by AC, AD by AC. So AD is tied to increase and AC is tied to decrease. AD is tied to increase and AC is tied to decrease. And for that reasons, this particular amount is tends to increase, and which is actually the CMRR, that means the common mode rejection ratio. Why common mode rejection ratio say like that way? Because you show this AD is increasing, AC is decreasing. How the op-amp is in the common mode rejecting? How a op-amp in the common mode, capability of op-amp in the common mode for rejections of two signals, that is actually defined by the common mode rejection ratio concept. As much as the common mode rejection ratio high, uh, the op-amp is good quality op-amp. If the common mode rejection ratio is high in case of operational amplifier, that means the operational amplifier is a good quality operational amplifier. Good quality. In here there is this particular op-amp 1, and this particular op-amp is op-amp 2. Between this we just compare and determine that this particular op-amp's quality is high, and this is the ratio of difference mode gain, and this is the AC, that is the common mode gain, that is the difference mode gain, and this is the difference mode gain, and this is the common mode gain, and the ratio of the difference mode gain by common mode gain, and you show that the difference mode gain is tends to high and common mode gain is tends to low. For that reason the CMRR is tends to high, this is high, this is low, and for that point of view it can be say that is the CMRR, how much the op-amp can capable to reject the signal in the common mode positions, that is actually the common mode rejection ratio concept. Thank you very much.